Training massive AI models and running billions of complex calculations requires rows of industrial server racks. As these systems scale, they pull electricity at rates that threaten global energy grids. The root of this power consumption is a physical inevitability called Joule heating. Processors rely on electrons moving through billions of silicon transistors. Every movement strikes atomic resistance, generating friction and heat. To perform calculations, computers rely on a basic switch, requiring one particle stream to act as a gate, allowing or blocking another. Electrons are perfectly suited for this. Because they carry a negative charge, they naturally repel one another. When two electron streams meet at an intersection, that repulsive force allows one stream to push the other, controlling the flow of data. The mass and charge of electrons are exactly what make logic gates work. But those exact same physical traits ensure that every calculation generates heat, forcing massive data centers to consume enormous power and water to keep the silicon from melting. We already have a way to move data without heat. Photons, or light particles, travel at the absolute speed limit of the universe. When we transmit data globally through fiber optic cables, photons generate virtually zero heat and encounter near zero resistance. But pure light cannot run a computer. Photons have no mass and carry no electrical charge. If you intersect two beams of pure light, they pass entirely through one another like ghosts. Without physical interaction, you cannot build a logic switch to control another beam. Researchers at the University of Pennsylvania engineered a workaround, starting with an atomically thin, two-dimensional semiconductor material. By trapping light inside this microscopic crystalline grid, they forced photons to strongly couple with electrons, creating a hybrid quasiparticle known as an exciton-polariton. Because they are part light, these hybrid particles move incredibly fast. Because they are part matter, they possess the charge necessary to interact with one another. Imagine two streams of hybrid particles approaching an intersection, a control beam and a signal beam. Their electron halves provide a physical repelling force, executing a logic operation. Because they move as light, friction vanishes, dropping energy consumption to just 4 femtojoules. At this scale, power consumption is nearly negligible. Offloading data transport to photons eliminates heat waste, allowing a chip to perform trillions of calculations per second while drawing less power than a smartphone clock. This mechanism directly addresses the most demanding workloads in artificial intelligence today. Systems running computer vision or autonomous monitoring process continuous streams of heavy visual data. Right now, when an AI monitors a chaotic city intersection, the optical data captured by the camera must be converted into electrical signals before the silicon processor can understand it. This continuous conversion adds latency and drains power. With photonic processors, the light hitting the camera sensor flows straight into the exciton-polariton logic gates. The AI analyzes the raw optical data natively, skipping the electrical conversion step entirely. This addresses modern computing's core trade-off. Electrons give us high interactivity, but generate high heat. Pure photons give us zero heat, but offer zero interaction. Exciton-polaritons merge the two. They deliver the matter interaction necessary for logic switching, while utilizing light transport to maintain near-zero heat. As we train increasingly complex foundation models, the physical limits of traditional silicon transistors are becoming a liability. Exciton-polariton chips offer a viable hardware upgrade, allowing us to scale the future of global AI without breaking our energy grids. Training